Alright, hello everyone. Today we're going to be talking about the photoelectric effect. So far in this series, we've talked about light as strictly a wave. You know, we've had Young's double slit experiment, which was supposed to confirm this for good, but Heinrich Hertz and his team in the late 1800s performed this experiment and they could not explain their observations in terms of wave behavior. So first I'll take you through the setup of the experiment, and then we'll go through and compare wave behavior and particle behavior. So what we have here is an electric circuit. We've got a battery that we can vary the voltage of. We have an ammeter to measure the current, and we've got a metal plate, that's this. And on the right hand side we've got a collector. We also have a light source, and this light is going to be incident upon the metal plate here. And it's important for me to tell you that we can vary the frequency and the intensity or the brightness of this light source. So how do we change the frequency? We put a filter over it or something and change the color of the light. And how do we vary the intensity? Well, maybe the light is on some sort of dimmer system. And this purple oval represents a vacuum chamber. So the idea is that as light hits this metal plate, it will release some electrons which can cross this gap and continue the electric circuit. So in this table we have a compare and contrast between the wave predictions and the particle predictions. So if light is acting as a wave, then light of any frequency should be able to release electrons. There'll just be a time delay between when the light is turned on and when the electrons are released. So those 2 points kind of rely on each other. It should take a bit of time for the energy in the electrons to build up. The wave model also states that brighter light should result in higher energy electrons, and that one electron is released after it's absorbed enough energy to escape the metal plate. The reason this experiment was so strange is that we'd been thinking of light as strictly a wave for almost 100 years. But nothing that we knew about light as a wave applied to this experiment. So it really shows a lot about the scientific method, and that just because we think something is the case doesn't mean it is. Nature has no obligation to behave in a way that we understand. So instead, what happened was there was something called a threshold frequency, or a minimum frequency, below which no electrons were emitted to continue the circuit. The energy transfer and the electron emission were instantaneous, so there was no time delay observed between the light being switched on and current flowing through the ammeter. And brighter light actually just resulted in a higher current, which meant a greater number of electrons were crossing the gap. And finally, one electron could only be released if the incoming light was above this threshold frequency. So electrons couldn't just sit there waiting to absorb enough energy, like in the wave predictions. They either had enough energy to be released or they didn't. Einstein in 1905 was the first person to reconcile this difference, and it's actually what won him his Nobel Prize, way before special relativity and all of that. He described light as wave packets called photons. So whenever I think of photons, I think of them like this little capsule, but they have intrinsically got this wave property to them at the same time. So you might have thought it was a bit counterintuitive throughout this video that we're talking about the frequency of light in order to prove that it's a particle, but this photon wave packet idea should hopefully resolve that. Now we can write out some equations to quantify our observations, but first we'll need to define a few terms. First we have V0, which is the stopping voltage. And you might have realized, if you were looking at this circuit diagram very closely, is that the negative terminal is actually hooked up to the collector plate, which means the electrons are flowing this way. And what that means is there'll be a buildup of negative charges around the collector plate, And that means there's a buildup of positive charges around the metal plate that the light is hitting. And that means that there's some kind of actually repulsive force. Remember, electrons are negative, and if they're flying towards a negatively charged surface, some of them might actually be repelled back to the original metal plate that they came from. So V0 is the lowest possible voltage when there's no photocurrent. At voltages applied below V0, there is a photocurrent flowing through the ammeter, but at voltages above V0, so say the stopping voltage is 2 volts, and we apply 5 volts, well, there's still no chance of a photocurrent because we're applying even more than we need to repel the electrons from the collector plate. We have F0, which is the threshold frequency that we talked about up here. We have W, the work function, and the work function just gives us an idea of the minimum escape energy that the electrons need to leave the metal plate. So I like to think of one parent formula, which depends on a few smaller formulas here and there. So we can write that the kinetic energy of the photoelectrons, or Kmax, is the energy of the photon minus the work function. Now, kinetic energy can be written in joules or in electron volts. If we're using joules, the kinetic energy is the charge on one electron times the stopping voltage. Remember, Q in this case is 1.6 times 10 to the minus 19. If you forget it, it's on your VCAR formula sheet. And if we're using electron volts, then the maximum kinetic energy is just equal to the stopping voltage. Now the energy of a photon is given by hf, or Planck's constant, times the frequency of the electrons. H is 6.63 times 10 to the minus 34 if you're using joules, or 4.14 times 10 to the minus 15 electron volt seconds. Finally, we have W, the work function, which is just hf0, or Planck's constant times the threshold frequency. So we can write one additional formula. If we take out h as a common factor, we can write that the kinetic energy is also h times the photon frequency minus the threshold frequency. So this was just a quick video outlining the photoelectric effect. We went through the key distinctions between the hypothesized wave model and the particle model which we actually observed. And we went through some quantitative descriptions as well. So thank you for watching, and if you have any STEM-related questions, it could be related to the photoelectric effect, it could be related to something completely different, please send us an email using the link in the description or leave a comment down below.